All right, today we're diving into a really beautiful piece of molecular engineering. It comes straight from a paper called Peptide Stapling with anion pi catalysts. Let's jump right in.
So, forget about car engines for a minute. What if you could build an engine, but on the scale of a single molecule? A tiny, tiny machine that could drive chemical reactions with unbelievable precision. Well, that's the wild idea we're going to explore today.
To even think about building a machine this small, you first need to know what parts you're working with. And in this case, our building materials come straight from biology itself.
Okay, so first up we've got peptides. You can think of these as nature's Lego bricks. They're these short, little chains of amino acids, and they are the absolute workhorses inside our bodies, doing pretty much everything from carrying signals to fighting off germs.
But here's the catch. In their natural state, a lot of these peptides are kind of like a loose string of beads. They're floppy, they're unstable, they don't really hold a specific shape. And that's a big problem because for a lot of jobs, you need a precise, rigid tool. You need a key that fits a lock perfectly. A wobbly string just isn't going to cut it.
So how do you fix a floppy string? Well, it's actually pretty simple. You give it some structure. You staple it.
And that brings us to this really clever idea called peptide stapling. And yep, the name is pretty much exactly what it sounds like. It's a chemical trick to create a bridge that locks or staples that floppy peptide into a very specific functional shape like the famous alpha helix you see here. This makes it way more stable and way better at its job.
Now, for their particular staple, these researchers used a very specific toolkit. At the center of it all is this flat, rigid molecule called a naphthalene diamide. We'll just call it NDI. Think of that as the hard plastic base of the staple. Then, to attach it, they put two special amino acids called cysteines into their peptide chain. These cysteines have these sulfur groups that basically act like molecular glue, sticking to the NDI core and creating this super strong, stable bridge that holds the whole thing in a perfect shape.
Okay, but here's where it gets really cool. This staple isn't just about holding a shape, it's also the engine. And to build this engine, the researchers had to break one of nature's biggest rules.
This really gets to the heart of the puzzle. See on the left, you have nature's go-to method for this kind of thing, cation pi catalysis. It's everywhere. It uses electron-rich surfaces to attract and stabilize positive charges. You can think of it like the negative side of a magnet. But on the right, you see what these researchers used. It's super weird, almost non-existent cousin, anion pi catalysis. It does the exact opposite. It uses an electron-poor surface, the positive side of the magnet, to stabilize a negative charge. This tool is basically nowhere to be found in biology.
Which leads to the big question, right? Why? Why would you go against billions of years of evolution and build your fancy new molecular engine using a tool that nature itself almost completely ignores? What's the advantage here?
Well, the answer lies in a piece of design that is just so incredibly elegant and efficient. It's all about making one component do two jobs at once. And this is it. This is the genius of the whole thing. That NDI molecule, it's not just the staple holding the peptide shape. Because it's an electron-poor surface, it is also the perfect engine to run that weird anion pi catalysis. It's brilliant. They designed a single part that is both the chassis and the motor.
And it wasn't just a clumsy fit, it was a perfect custom fit. The paper says it right out. The dimension of core-bridged NDIs matches that of one turn of an alpha helix. It's like they designed an engine block that just happened to slot perfectly into the car's frame with zero modifications. It's just beautiful molecular design.
Okay, so the design is amazing on paper. But does this little molecular machine actually, work? Let's check out the results.
So, to test their catalyst, the team set up a simple contest, a chemical reaction with two possible ways it can go. The catalyst's job is to make more of product A, that's the good stuff we want, and less of product D, which is just a useless byproduct. Success is just a simple score, the ratio of A to D. The higher the score, the better your engine is.
So, how did it do? Well, this chart really tells the whole story. On the right, that's the control peptide, the one without the staple. It gets a score of about 3. Not great. But now, look at the bar on the left. That's our NDI stapled molecule. Its score? 35. That's not just a little better, it's over 10 times more effective.
And a score of 35 wasn't just a small win. It turns out to be one of the highest performance values ever reported for this kind of catalysis, outside of complex natural enzymes. So they didn't just build an engine that worked, they built a record-breaking, high-performance racing engine right out of the box.
But was this just some kind of lucky accident?
Well, the next set of experiments proved that this incredible performance was all about meticulous, deliberate engineering. This slide is where you can really see the power of precision. The researchers started to deliberately break their own winning design just to see what would happen. And look, when they made the staple ring a little smaller, the activity almost disappeared. When they made it a little bigger, performance just dropped off a cliff. And here's the kicker. They simply moved the active part of the engine over by just one spot. The result? All catalytic activity gone. The engine just completely died.
So the big takeaway here is that the catalyst's incredible power came from its exact engineered geometry. Every single atom was in the right place for a reason. This wasn't luck. This was brilliant architecture on a molecular scale.
But the story has one final, really surprising twist. As a final test, the researchers just wondered, hey, what happens if we make the peptide chain a little bit longer? You'd think adding more stuff might mess it up, right? Nope. It did the exact opposite. Performance skyrocketed to a score of 63. By giving the helix a bit more room to form, they accidentally made their record-breaking catalyst even better.
What this work really does is give us a powerful proof of concept. It shows that we can use these so-called unnatural chemical tools to build tiny, incredibly powerful machines with unbelievable precision. It just opens up a whole new way of thinking about design. Which, of course, leaves us with one heck of an exciting question. What other molecular machines could we build with this new, powerful design toolkit?